Welcome back. Let's continue with our lecture on general theory of relativity. In the last lecture, we have some of the aspects of special relativistic dynamics. Namely, we have defined 4 velocity and how to convert 4 velocity to Newtonian 3 velocity and similar notation. Let's continue with the special relativistic dynamics in a little bit more detail. This lecture is very important because here we are defining what is called the energy of a physical system with respect. Now onwards, observer essentially have to be a time light because there cannot be a massive particle or a lab or a person who can make a measurement can move at the speed of light. So the speed of light is only for the massless particle. So observer necessarily means a time light and its velocity is normalized. That is all the time we are using proper time as our parameter. Let us continue with the lecture. This is part of course PH4205 at IISER Calcutta. Now let's first look at the relativistic moment. Earlier we have seen that the relativistic momenta is given by derivative of Lagrangian with respect to x dot mu. So that is a standard definition of generalized momenta in Lagrangian mechanics, and we have seen that the same holds good. Particle moving in a curvilinear coordinate system, we apply same principle in the case of relativistic mechanics. So let's consider the simplest Lagrangian, that is a Lagrangian of a free particle in a Minkowski space. The Lagrangian is given by, in this case we retain m such that there is no confusion created. Lagrangian is given by m by 2 into t dot square minus x dot square minus y dot square minus z dot square. In short, we know that it is basically v dot v, or the dot product of 4 velocity with itself, that is m by 2 g mu nu x dot mu x dot mu. We have seen that the 4 velocity is defined as u mu is equal to t dot x dot y dot and z dot. We have also seen it can be written in a compact notation gamma into 1 into u, where u is the spatial velocity, and we have seen that the gamma is basically dt by ds. If we use arc length as parameterization, we normalize the velocity for time-like curve. That is u mu is equal to 1, and for null we have u mu is equal to 0. Now from this we get that p mu, that is a generalized momenta, is equal to m into g mu nu x dot mu. Let us raise the index of generalized momenta to upper. For that we have to multiply it by g mu nu upper, and here we have p mu upper is equal to g mu nu p mu, that is given by, we substitute for the lower index from expression here, what we have m into g mu nu into g nu rho into x dot rho. We know that the g mu nu upper and g mu nu lower are inverse of each other. We get a delta mu rho, and that can be simply written as a m into x dot mu. So we see that for a simple particle, we still go through the definition very similar to Newtonian definition. In the Newtonian mechanics, what we have is a momentum is a mass into velocity, and the same thing here works, except that we have a time also a dynamical variable, and we have generalized momentum upper indices is equal to m into u mu, and that is 4 velocity of the particle. So this is a general understanding, just reiterating that the standard definition in physics work through here. And let us look at the definition of a rest mass of a particle is given m square is equal to p mu p mu. So this is one of the fundamental definition. You might have seen in some places people call the effective mass when transformed to Lorentz frame and all that. Those are generally lead to confusion, and there is no standard definition for them. We have only one standard definition for rest mass, and rest mass is given as a scalar p mu, and that does not change from frame to frame, and it is always going to be same irrespective of the frame which you observer. And we have a habit of putting that equal to 1 for convenience, but in this lecture we will retain that m as a m itself. Similarly, for the null, rest mass is 0, simply because p mu is equal to 0. Generalized momenta for light rays is considered to be 0 because it propagates along null direction. Now let us look at the rest mass and all. We have a frame with respect to our particle is rest. That means for velocity of the particle with respect to frame, u mu is equal to 1, 0, 0, 0. The time always propagates no matter what you do. Spatial motion need not be present. The spatial velocity can be 0. That is why we have rest with respect to the frame is given as a only time component, that is 1, and rest of the spatial velocity is 0. In such case, momenta is given by p mu is equal to m into 4 velocity, that is equal to m into 1, 0, 0, 0. Now it is equivalent to having your particle rest in the frame and your observer is also rest in the same frame. So this is basically concept of the rest observer and rest frame. Now we have identity. It is simple to compute the rest mass. M square is equal to p mu. So that is well satisfied here. There is no ambiguity. If the particle is moving with respect to the frame, so it could be the observer moving with respect to frame, doesn't matter. Let's call the particle is moving with respect to the frame. Then the 4 velocity of the particle can be written with this form, that is u mu is equal to gamma into 1 into v, where v is the spatial velocity. We have clearly defined this notation earlier, and also we have p mu is equal to m into u mu, that gives you m into gamma into 1 minus v square. There is an error here. It should be mu. So with the standard definition, m square is equal to p mu. Again, it comes out to be same irrespective of velocity of the particle. In this case, you have a particle moving or the observer. You can consider this one itself to be particle and moving with respect to the frame and with the 4 velocity. Now note that we are using the unit c is equal to 1, which means that E is equal to m. There is no famous formula E is equal to mc square. We simply have E is equal to m because we are taking c is equal to 1. So that is called the rest mass energy of the particle. So how does this come about? It is usually referred to as a zeroth component of energy momentum vector or 4 momenta, which is generally taken as a mass or energy. However, since we have seen that in these two cases, in the first case, mass is zeroth component is simply m. In the second case, we have seen that it is m into gamma. It is not convenient energy of the particle defined like that. We need a covariant definition for energy of 4 momenta. We cannot rely on calling it as a zeroth component because the component themselves do not have any specific meaning because they change from frame to frame. One need to have frame independent way of defining energy of a particle. That definitions are usually called the covariant definition, which can easily transform from frame to frame without having to deal with any confusion. Let us go ahead and see how to define the energy of a part. When we define an energy, we generally have a two aspect. One what we call is an observer, another which we call is a 4 moment. This is usually combination. You need an observer who measure the 4 momentum. This is basically an experiment to measure momentum of the particle. Once we have a 4 velocity of an observer and a momentum, the momentum could be of a particle or a light or any physical system. On the other hand, observer have to be time-like and whose velocity is normalized, so to have a proper definition. In such case, the energy of the 4 momentum p mu with respect to the observer v mu is given as p mu v mu. So this is a scalar and one can easily transform from one coordinate system to another coordinate system and doesn't depend on the coordinate system. It is often considered that the zeroth component of 4 momentum is the energy. Let us see our new complex definition match with it. Now, in order to understand this concept of energy observed by an observer, let us consider the various possibilities. We consider the physical system to be a massive particle moving. moving. Later let us consider what happens to the null. Let us first consider our P mu is defined by the massive particle. That is, P mu is given by m into v. In this case, in a frame, we have a two entity. One is a time-like observer who is rest with respect frame, and we have particle with mass m, which is also rest with respect to the. Now we consider the energy of the P mu with respect to observer v mu. We can simply compute that and we get E is equal to m. So C square is not there, C is equal to 1. So you see that in this case, this is a zeroth component. This is considered to be energy and momentum, where you have a honey which is a highly energetic, and then you have an observer who is planning to have the honey or energy from that and trying to measure it, how much energy it has. So basically the dot product, which gives the force velocity of this and the momentum, will give you m, that is if both are rest with respect to each other. And this is a frame which is not necessary to bring in, but we always refer to with respect to frame, both velocities are rest. Now let us consider the next case. In this case, we still consider a frame with the observer rest. That is, time-like observer is rest. That means whose force velocity is given by 1, 0, 0, 0. Now the particle is moving with the force velocity u mu. That is, let's call it as a gamma p, means gamma corresponding to the particle. We have a velocity is given by 1 into spatial velocity u. Now let's compute the force momentum of this particle, that is given by m into u mu. P mu is equal to m into gamma p into 1 u. We take the dot product between P mu and V mu to get the energy of a force momentum P mu. That energy here is m into gamma p. Here the effect of motion of the particle comes in and the energy is basically changed. So in the pictorial way, you have an observer who is still rest. On the other hand, your physical system with the energy momentum P mu is moving with respect to the frame. So energy measured with respect to them will have an additional gamma p factor. Now let's look at the next example. In this example, let's consider frame in which a time-like observer is moving with the velocity v mu. It can be written as a gamma o, that is gamma corresponding to observer, and a spatial velocity v. We have a particle with the force velocity u mu, which is rest with respect to frame, whose force momentum is given by m into u mu, and that can be written as 1 to 0 because it's not moving in the frame. Now we again calculate the energy observed by observer O to the particle P mu, and then we get quantity as a m into gamma O. So that is because in this case particle is rest with respect to frame, but observer is moving. So that effect also comes in. In this case our observer is moving, maybe in arbitrary direction, not sure where the energy is, and here is the energy of the rest particle who is nicely having a good nap with a pot full of energy. So that is, if this observer try to get this energy, he will have a gamma factor multiplying to this. So this consistently comes in all the cases. All the detail I am working through is to show that it doesn't matter either particle is moving or velocity is moving. It basically means that the relative velocity which matters. The frame in between is a meaningless if you can directly consider these two and their relative velocity, and the gamma factor corresponding that would appear in here. Now let's consider the next case where the both observer and the particle which is moving. The observer is moving with the force velocity which is given by gamma O and the spatial velocity v. Particle moving with the force velocity u mu, which is gamma p, and u is the spatial velocity. Now force momentum of the particle, as we seen, is given by m into u mu. And now we take the dot product between the observer's velocity to the force momentum of the particle. What we get is little bit complicated. You can see that velocity addition rule comes in. We have seen that earlier velocity addition, gamma get multiplied and then you have 1 minus v dot u. So it depends on which direction they are moving in. So you see that observer and this relative velocity, which it matters, and dot product also matters. In this case, what you see is both of them are running around in the frame, and both of their four velocity would affect the measurement of the energy. This is to show that how physical system behaves based on the observer and what you observe. It's not just in the quantum mechanics that the observer going to affect observation. Even in the special theory of relativity, observer's four velocity is also going to contribute to the energy observed by the observer of a physical system. Let us continue how this formula is going to affect the light propagation. In this case, what we consider is a time-like observer, either 1 or 2, who sees a light with the four momentum p mu, and then the energy observed, how it differs based on the velocity of the observer or the source, which will introduce the Doppler shift. Let's take the p mu with the four momentum corresponding to the light. That means it is a null trajectory. We have p mu is equal to 0, or u mu is equal to 0. That is basically is the relation of the four momentum. We have seen that for light we can write it like where k is a spatial unit vector, and the condition p mu is equal to 0. Once we write p mu in the following fashion, and p mu is a null vector, what we get is a E0 square is equal to k dot k. So this basically gives the relation that p mu is null, means that the energy is related to the direction along which light propagates. Let's first consider an observer U0 who is rest on the frame. That means that the source of light and the observer is rest. That is why he is given another index here, which means that 0 is not moving or rest with respect to the frame or the source of light, whose four velocity can be written as a 1 to 0. In the Minkowski space-time, rest observer is given by this. There is a gamma factor which is 1. Now you take the dot product, we see that the p mu u mu is equal to E0. That is a zeroth component in this case, because of the observer is rest with respect to the frame. If observer is moving, it is going to change. Let's consider another observer who is moving with respect to this source of light, whose four velocity is given by v mu. The four velocity of the observer is given as a v mu, which can be written as a gamma and the spatial velocity v. From our definition, energy observed by this observer E is equal to p mu v mu, that is given by E0 into gamma into 1 minus v dot k. This is basically the formula of a Doppler effect. The Doppler effect depends on the two factors. One is a gamma factor, and second is the direction of propagation of light and the spatial velocity of the observer. If the spatial velocities are aligned, then it is going to take the maximum effect. If they are orthogonal to each other, then there is not going to be any change in the energy observed. So this we have seen from time and again, various examples such as train going, and you might have yourself listened that how frequency changes when train whistle when you are standing on a platform and observing it. So is the light also affected by this. Let us pictorially look at in the space-time diagram. You have frame O in which you are observing. First one is a rest observer whose four velocity is given by v mu, which is 1, 0. Is just following time axis. On the other hand, we have a light ray which is propagating in that frame, and that is always going to make a 45 degree with respect to time axis. So the angle between a rest observer and the light ray is going to be 45 degree. On the other hand, when a train or moving observer comes in, who is going to move with the four velocity given by gamma into spatial velocity v, depending on its velocity, is going to make some angle with respect to the time axis. We have seen that angle would change based on the velocity. If the velocity is c, then it is going to be 45 degree. That can't be done for a massive particle or a time-like observer. So this observer is time-like, so his velocity is always less than 1 or c. And now you compute the energy observed, so it is going to have this factor of gamma into 1 minus v dot k, And here we can both see that gamma factor and the propagation direction of light and the direction along which observer is moving appears, and this is how we get the Doppler effect. The Doppler effect is basically light being observed by either a rest observer or an observer is moving. Okay, let us go ahead and do some more relativistic mechanics. One of the standard problems which we deal with the relativistic mechanics is a collision creation and annihilation. This is a case where you have two particles come and collide, resulting in the two particles. So this is basically collision experiment where you have two particles with the four momentum p mu and q mu come and collide, resulting in the two particles whose four momentum is given by p bar mu and q bar mu. So this is collision problem. This could be your particle accelerator where two particles come and collide and producing two particle or more particle. This is a simple case of two particle only. On the other hand, you could have another way where it is called the creation. You can also have an annihilation. In the creation case, 1,4 momentum comes and then it creates 2,4 momentum, P bar and Q bar. So you can have a reverse of this. It is simply time reversal of this. What you call is an annihilation, where 2,4 momentum come and collide and then they get destroyed and producing a single particle P mu. Sometimes common sense to take P mu to be null, because this is what we call essentially particle creation, where two particles would annihilate to give light, or light can be made to produce two particles. Important equation here is the momentum conservation equation before and after the collision. So this entire formalism is called the collision of particles. So we have momentum balance equation, which is given as before the collision total momentum is given by P mu plus Q mu, and after the collision the total momentum is given by P bar mu plus Q bar mu. So if the momentum is not lost during the collision, then you have momentum balance, and the total momentum before the collision should be equal to the total momentum after the collision. So this is a fundamental equation with which we work. And then we can take the various approximation. We can have an example like time-like particle decay into two null particles. Single time-like particle comes in and then it just goes into two gamma rays or null particles. So in this case, we have to consider Q mu to be 0 because there is only one particle and that particle is a time-like. On the other hand, balance equation state that you have P bar and Q bar both are to be null. Since the first particle, that is P mu, is a time-like particle, we can have a mass, rest mass of that is P mu is equal to m square. On the other hand, both the resulting particle, that is P bar and Q bar, are null, so that is P bar dot P bar is equal to 0 and Q bar dot Q bar is equal to 0. Now we can choose a frame. You can choose the frame rest with respect to the time-like particle, because time-like particle is involved, then it is easy to choose a frame. If there are no time-like particle, then one has to construct an artificial observer. So you have P mu is given as a m into 1, 0. So that is the rest. We got to use this momentum balance equation to find out the various properties of P bar and Q bar. So what we do is we write that as energy and the spatial direction. That is what is mainly involved for a null particle, and it also satisfies the condition that E square is equal to, it should have been k dot k, it's not V. So there is a few more error here. It says that it is a null part. Once we have this, we can cook this up. M square we have, and then we taking the dot product, we get the P mu bar Q mu bar is equal to E square minus Kp dot Kq dot. So that is what the direction along which the resulting gamma ray propagates. So that we can write in terms of mass of the particle. So that is m square is equal to 2p p bar dot q bar, that is equal to 2 into EP bar EQ bar minus k dot kp bar dot kq bar. So this can be used to compute direction along which the photons are propagating in the collision given their energies. So this is how various collisional problems are computed. You know the mass of incoming particle, you know the energy of the photon, then you can find out the direction. On the other hand, if you don't know the energy, you can simply calculate the direction along which light propagate, then you can easily calculate the energy of the photon. So we are basically assume that we are producing the identical photon. So these are various approximation to simplify this momentum balance equation. Now let us look at another problem. In this problem, a time-like particle goes into two time-like parts. So this is like an experiment in which you have collision being treated. You can reverse this and say that two time-like particle going to, and then you are going to produce a single time-like part. So you can both have a reverse and forward. All you have to treat is momentum balance equation. So you have q mu is equal to 0. Let's take problem. So P mu is equal to P bar mu plus Q bar mu. So this is a single particle divided into two. We have time-like particle. P mu is equal to m square, mass of the particle. We can also have a mass of the resulting particle. Let P bar comes with the mass m1 and the mass of second particle to be m2. This should have been m2. Or we can restrict them to be same. It doesn't matter. This is an example to show how various physical properties can be related during and after the collision. We can go ahead and see what happens. All we have is a momentum balance equation. Now we can take the dot product with itself, and then what we get is m square is equal to m1 square plus m2 square plus the dot product between the P bar and Q bar. So this is a basic equation. Again, use particle P mu to be having a mass and gamma P, and then you can have particle P bar. In the same way, you can write it in terms of gamma and its spatial velocities, and then we can substitute and relate their velocity. We take case to show that. Let's take the lab CERN to be the rest frame in which all these particles are moving with. You can see that how these are done if you are colliding two particles in a high energy accelerator. So energy which we are getting is basically computed based on this momentum balance equation we have is given by P mu U mu with respect to the observer in the lab. Then we can associate all these equations. What we have is m square is equal to m1 square plus m2 square plus 2 into m1 m. In this equation, what is important is the dot product between the P bar and Q bar, which would acquire the gammas corresponding to P bar and Q bar. We have seen that this is compared to our earlier example where we had a rest frame and both time-like observer and the core momentum was moving. We had this dot product. We have had a dot product like this, and then eventually we get the condition that the gamma P bar, gamma Q bar, and 1 minus V P bar dot V Q bar is equal to 1. And then we get the angle between the P bar and Q bar. To relate to the experiment in particle physics is that you have one particle, in this case decays into two time-like particle observed by the lab, and you have only physical measure. In this case, if you already know the mass, then you have an angle between them. The angle is measured with respect to the spatial velocity of the two particles which are produced, which is basically is a measure of this experiment. However, the CERNS experiments are extremely complicated, not because of, though the basic equations are same, you may have a single particle because it carries an extremely high energy, and once it is interacting, it would produce not one or two particles, it is going to produce thousands and millions of particles. So when you have a two proton colliding, they literally will produce a huge shower of high energy particles. Some are stable, some are unstable, eventually decay into another particle. So you will have a whole zoo of particles with various four velocities going in all direction, and one has to compute them and then do this balance equation. Though on the left hand side you have only two terms, that is two protons colliding, on the right hand side you will have thousands and thousands of four momentum which need to be balanced, and then you can have an angle with respect to all of them. So it is an extremely complicated both in terms of measurement and modeling because of a large number of particles produced in the system. That is how use the special theory of relativity to compute the various aspects of collision, creation, and annihilation, where more complex version being used in the experiments such as particle physics accelerate. Let me stop here and continue with some of the mathematical aspect required for the general theory of relativity in the next lecture.